All right, hey guys, me again. So now we're on to the second video, and now we're on to the math. So now that we're on to the math, I'm going to be using my cell phone. Try really hard to keep my hand stable. I've ordered a phone holdy thingy, but that hasn't come in yet. So that'll probably be better than my hand, but don't have it right now. So we're going to go back and forth between the slide and my lovely piece of paper so that we can get this worked out. Okay, so first question, explain what the pH of a buffer that is 0.12 molar lactic acid and 0.1 molar in sodium lactate. It says for lactic acid, the Ka is 1.4 times 10 to the negative fourth. Okay, now I promised you that we would use this, but we're also going to use the old school common ion question as well. Hi, Luna. Go away, Luna. And we're going to get this question solved. All right, so starting out, we're going to use the common ion one. Okay, so we have a generalized acid dissociation. So HA dissociates into protons and anions. And we're starting with ICE. Okay, now, initial concentration of the acid is 0.12, right? Initial concentration of the conjugate base is going to be 0.1 because this is an ionic compound. The sodium ions correlate to a strong base, so we're really just getting that conjugate base from that. So 0.12 for the acid and 0.10 for the base, and then we know we have no protons to start out with. Okay, so negative X for the reactant, for the change, positive X for the products. So this would be 0.12 minus X. We have X, and then 0.1 plus X. Okay, if we set up our Ka expression, Ka is equal to concentration of the proton times the concentration of the conjugate base over the concentration of the acid. Okay, but what we're going to do is we're going to assume that this little negative X right here isn't going to make much of a difference. And we're going to assume that this positive X right here doesn't make much of a difference. Okay, to make our world a lot simpler. And we'll check our assumptions later. We know how to do that. So, all right, plugging in. So we got X times 0.1 divided by 0.12. And this is equal to the Ka, which was given in the question. Okay, so that's 1.4 times 10 to the negative fourth. And honestly, at this point, you just need to get your handy dandy calculator and start plugging this stuff in. Okay, so we could cross multiply, right, which is what I would really sort of recommend-ish doing here. So we got 0.12 times 1.4 e to the negative fourth, and then that's going to end up being divided by 0.1, and we get that X is 1.68 times 10 to the negative 4. So X is the concentration of the proton and is 1.68 times 10 to the negative fourth molar. But that doesn't answer the question because the question asks for pH. So pH is the negative log of the concentration of the proton, right? So now we can go back to our calculator and just negative, where's the log? Log of the answer, and we get 3.78 because 2 sig figs, so 2 decimal places. Or sorry, 3.77. I am rounding wrong. Sorry. 3.77. Okay? Very long way to do this. Now let's do the shortcut. All right? The shortcut is just using the stinking Henderson-Hasselbalch equation. All right. So pH equals pKa plus the log of concentration of base over acid. Again, why are we able to do this? Well, because we did this. We're already saying that equilibrium is initial. If we're going to scratch out the minus X and plus X, why even worry with the ice table in the first place? All right, cool. So pH equals pKa. So the pKa is going to be the negative log of Ka. So, and our Ka is 1.4 times 10 to the negative fourth. All right. and then plus the log of the base is 0.1, right? And the acid is 0.12. So we got 0.1 over 0.12. Okay, you can do this in small chunks if you want to. All right, so negative log of 1.4 e to the negative 4 are pKa. And hold on to some extra, decimal places here because you're not at the end, so don't just chop off this answer. So I get 3.854. Okay, that's enough. That's an extra one. Plus, we'll go ahead and do the other part. So log of 0.1 divided by 0.12. Okay, and we get a negative 0.0792. Okay, so not very much difference, but 3.854 minus 0.0792, and we get exactly 3.77. So as you can see, they are the same answer. Which one took more work, right? I know I don't even really have to say this, so now you know which method to use. Okay, perfect. And all that is here on the slide. Okay. Ta-da. Okay, cool. Let's do another one. So calculate the pH of a buffer composed of 0.12 benzoic acid and 0.2 molar sodium benzoate. Okay, so pH equals the negative log of Ka, which in this question is 6.3 times 10 to the negative 5, plus the log of the base, which the base again is going to be the ionic compound, right? Because the ionic compound is what's giving you that conjugate base anion, okay? So base 0.2, acid 0.12. So base is 0.2, acid is 0.12. Okay, and if we put all of that into our calculator, so negative log 6.3 e to the negative 5 plus the log of 0.2 divided by 0.12, we get 4.42. All right, so the pH here is 4.42. Okay, now this one has a much lower pH, so let's talk about it. So this has this one actually has a higher pH, a higher pH than the last question. But look at those Ka values. I told you that it was dependent upon initial concentrations and the Ka values. Lactic acid is a stronger acid, thus we're able to buffer at a lower pH than, say, benzoic acid, which is a much weaker acid. Okay? All right. And then we've got another question here. So it says, how many moles of ammonium chloride must be added to 2 liters of a 0.1 molar ammonia solution where the Kb is 1.8 times 10 to the negative 5 to form a buffer whose pH is 9? So now what they're doing is they're not giving us one of our concentrations, which means if they're not going to give us one of our concentrations, they have to give us the pH. So they do give us the pH here, and we know that the pH is 9, okay? So pH equals, so 9 equals the negative log of, we want the negative log of Ka, but what do they give us in the question? They gave us Kb. So we know how to relate Kb to Ka though, right? Because Ka is equal to Kw divided by Kb, and I told you guys, unless you are told otherwise, to assume that Kw is at 25 degrees Celsius, you know what it is, right? So this is 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th, okay? So 1 e to the negative 14 divided by 1.8 e to the negative 5, and we get 5.556 times 10 to the negative 10. Again, we're holding on to a little bit extra because we're not at the end of the question, right? So 5.556 times 10 to the negative 10, okay? So there's our negative log of Ka. Now, plus the log of, which one is it that we don't know what it is? Ammonia is one of the most common weak bases. Okay, so there's your base, and then that's ammonia, and then ammonium, the conjugate acid of this, okay, so it's the acid that we don't know, we know the base, okay? So then we know the top part of this fraction is going to be 0.1, and we know the bottom part of the fraction is an X, because we don't know what the acid concentration is. Okay, so from here, it's a little bit of math, right? So we have 9 is equal to, I'm going to go ahead and do this negative log. So negative log of 5.556 e to the negative 10. And I get 9.255. All right, so 9.255 plus the log of 0.10 divided by x. At this point, you could just subtract, right? 9.255 minus 9.255. All right, so 9 minus 9.255 is equal to negative 0.255, which is equal to the log of 0.1 over x. At this point, you need to get rid of the log. How we're going to get rid of that is basically you need to take the opposite of a log, which the opposite of the log is taking 10 to a number. So 10 to negative 2.55. Sorry. 10 to negative 0.255. Wrote that wrong first time. Is equal to 0.1 divided by x. Okay. And 10 to the negative 2.55 is 0.556. Okay, 0.556. And that's equal to 0.1 divided by x. So now we multiply by x. You could basically swap those two terms. So x is going to be equal to 0.10 divided by 0.556. So 0.1 divided by 0.556. And we get 0.180. And this is a concentration, right? So this is molarity, but this is not what they asked us for. If we go back to the question, they said how many moles must be added to 2 liters. So molarity is equal to moles over liters. Thus, if we rearrange this equation, mole is equal to molarity times liters. Okay, so this is going to be, sorry, my paper's trying to slide on me. 0.18. I'm having to write very softly as not to slide the paper. 0.180. Just stick it under my laptop. All right. Dagnabbit. Times 2. Okay? So 0.18 times 2 is 0.36. All right? So, and this is now moles, right? Because we did molarity times liters, so we get a unit of moles. There's another question here on the slide. It's just more of the same thing. It's more or less for you to practice yourself. If you have questions about how we got from here to here, please post them in the discussion under assignments, okay? So the reason why we're using the discussion in the assignment section is so I don't get billions of emails asked where you guys ask the same question, okay? This also gives you a chance to talk amongst yourself, so I really do encourage you to use that discussion board area in the assignment section, okay? There will be a discussion for every single set of lectures, so please go in and discuss, talk amongst yourselves. Remember, I'm going to be in that discussion from 1 to 3 every day. Now, you're not my only class, so I will be sort of cycling between discussions, so if I don't answer within 30 seconds, I promise I'm there and I will get to you, but please make use of those discussions. I really think that's about the only way we can try to duplicate a classroom environment. So, all right, this is the end of video number 2. We are still not done. More videos to come. We're going to go back to screencasting. I'll see you in a few seconds.